This clip explains how to apply an F-test to test multiple restriction in a linear regression model. Let's look at this model. We have log wage of a sample of female employees as the dependent variable and experience, the number of children younger than 6, the number of children at least 6, and the age of the woman's husband as explanatory variables. So this is the full model. If we look at these three variables, the two kids variables and husband's age, they are variables that describe our family circumstances of the female employee, and individually all these variables seem to be not statistically significant, and we may ask the question whether as a whole group these variables are indeed insignificant. In other words, we want to test the null hypothesis that beta 2, beta 3 and beta 4 are equal to 0. The alternative will be that at least one of them is unequal to 0. So let's think about how the model looks like if the null hypothesis was true. Then we would have as explanatory variables only the constant and experience. So that would be a restricted or shorter or smaller model. Of course, we know that restricted models will have worse fit. So it's important to understand the following. The unrestricted model, which is actually the yellow model, not the blue model, will always fit better than the restricted model, which is really the blue model, not the yellow model. Formally, we say that residual sum of squares restricted are larger than residual sum of squares unrestricted, or that the difference between the two is always going to be larger than 0. That is very important to understand. The question is, however, when we impose these restrictions, is that this difference, which is going to be larger than 0, actually significantly larger than 0? That's the question we want to answer. And as good econometricians, we know what we need is a test statistic to establish that. Now, at the core of the test statistic is going to be this loss of fit, the difference between the residual sum of squares between the two models, the restricted and the unrestricted model. So this is what we call the loss of fit, but we standardize this by the number of restrictions imposed. In our case, this was 3. That will be our numerator of the test statistic. In the denominator, we will have the residual sum of squares of the unrestricted model divided by the degrees of freedom for the unrestricted model. So this is what we call the F-test. And we know we need a distribution for this F-test. And it turns out is F distributed with Q and degrees of freedom U degrees of freedom. So there are two sets of degrees of freedom for this test statistic. Here, the DOFU is actually n, the number of observations, minus the number of coefficients in the unrestricted model, and they were 5. There were 5 coefficients estimated. So the decision rule is as follows. Reject H0 if the F-test is larger than a critical value coming from that F distribution. So let's just sketch a little F distribution. It looks a bit like this, depending on the degrees of freedom, but it's only on the positive line, and that is because this loss of fit, that term will always be positive, and the denominator will always be positive as well. So F-tests will always be positive. And the critical value will be determined by an alpha, a type 1 probability. And if our F-test exceeds that critical value, we will reject. So let's put some meat onto the bones. Let's say the alpha is 5%. Now our F distribution, what degrees of freedom does it have? We have 3 restrictions, and the degrees of freedom of the unrestricted model is 428 observations minus 5. I hadn't given you the 428 before, so 423 degrees of freedom. What we now need is the critical value for this distribution. So we'll go to a table. For an F distribution, we look at the subtable for alpha of 5%. Then we have numerator degrees of freedom. We, in our case, they were called Q. And we had 3, and then denominator degrees of freedom 423, somewhere between these numbers. Let's just use the larger one. It doesn't really matter which one you use. So it's 2.61, which is the critical value. To be able to calculate the test statistic, we now need the residual sum of squares, and I'll just give you the numbers. That would come from the statistical software package, of course. What we then need to do, let's just state the number of restrictions and the degrees of freedom u again. Then we just need to plug in these 4 numbers into our F statistic. Once you do that, you get a value for the F statistic based on our data of 0.8567. So relative to our critical value, that's to the left of the critical value, it's smaller, so it's in the do not reject region. Only if it was larger than 2.61 we would reject the null hypothesis. Our conclusion is do not reject H0. What does that mean in the context of our example? So that restriction, it is valid to impose that. So it's really the restricted model, the blue model, that is sort of the relevant model. We don't need these 3 variables in our model. So why not solve this little practice quiz? We have another linear regression model, this time with 3 explanatory variables. Again, years of experience, but now this time husband's age and husband's wage. And the null hypothesis is that these 2 associated coefficients, beta 2 and beta 3, are restricted to 0. And the question you ought to answer now is which of the following are the correct values for Q, the number of restrictions, for instance, are they 3, and the degrees of freedom for the unrestricted model, for instance, are they 423. And here are 3 other possible solutions. Recall that Q and DOFU are not only important for critical values, but also important in the calculation of the F statistic. So, pause the clip and try and solve it. Here's the solution. As far as the number of restrictions is concerned, the only way to get that is to go to the null hypothesis. Here, in our null hypothesis, we are restricting beta 2 and beta 3 to 0, so we have 2 restrictions, meaning solutions A and B are wrong. The degree of freedom for the unrestricted model is n minus the number of estimated coefficients. Here we have 4, so it's n minus 4, altogether 424. Therefore, there's only one correct solution, and that is solution C.